Hello everyone, this is Fiza friend from group 316. Today's my topic is the coil and the globule. The primary or chemical structure of a macromolecule chain is fixed. The chemical bond in it do not exchange places. The presence of linear memory in the factor responsible for certain features in the properties and structure of macromolecules. The conformational changes of macromolecule, that is, the rotations above single bonds. As a result of much rotations, a coil is formed which is the looser, that is, its size is the larger, the lesser flexible is the chain. The meaning of persistent chain length is as follows. A chain segment shorter than D may be regarded as a rigid rod. The segment of the length being capable of rotation independently of one another, they are freely jointed. Theory gives the following value of the mean square chain length. This is the equation. Even a very rigid chain is coiled up if it is very long enough. The link in the coil which are far away from one another along the chain can come closer together, so-called volume effect thus rises. Flow. The interaction of monomeric unit in the coil are similar to the interaction of molecule in a real gas. A strong repulsion at small distance, as a result of which two monomers cannot be in the same place, and a weak attraction at large distance. At theta, temperature is similar to Boyle's point of a real gas. At temperature greater than theta, the repulsion predominant, a good solvent, and the temperature lesser than theta, there are predominant attractions, a poor solvent. The coil is dilated or contracted. The density distribution in the globule. A macromolecule coil as a fluctuating system is characterized by a density correlation, a quantity which relates a change in density at one point is space occupied by the coil to change in density at another point. It turns out that the same order as the size of a coil. The presence of large correlation radius is due exactly to the linear memory is the chain, but if this is so, then the density of the coil is not its thermodynamic characteristic. It has no reliable constant value. The macromolecule coil is continuously fluctuating and its fluctuations are macroscopic. This is the graph which is related to the density distribution in the globule. The flow theory regards a polymer coil as a cloud of monomer neglecting their union into a single chain. However, it is necessary to deal not with monomer-monomer interaction, but with interaction between chain proteins. A polymeric coil may be depicted as a cloud of quasi-particle to a quasi-monomer. The theory proposed by a Koklov is rigorous and provide a good agreement with experiment. If a strong attraction occur between the chain links at temperature less than theta, or the coil is acted on by a external compressing field, it is compacted into a tight coil structure, a globule. The process that takes place in similar to the condensation of a gas to liquid. The theory of coil globule transition has been worked out by a Lifts and Grossberg and Koklov. Coil to coil globule transition. First order phase transition driven by a change in first temperature, second solvent quality, third polymer concentration, and fourth ion strength. Theories. Fleury-Huggins theory described polymer-solvent interaction and phase separation. Fleury-Runner's theory accounts for polymer elasticity and swelling. Lattice model stimulates polymer chain configurations on a lattice. Self-consistent field theory describe polymer chain behavior in a solution. Biological implications: protein folding and misfolding. Coil to globule transition relates to protein functions. Second, chromatin condensation transition regulates to gene expression. Third, DNA packing transition influence DNA accessibility. Fourth, biopolymer self-assembly. The second topic is methods of investigation of macromolecules. Macromolecules of the any chemical structure are characterized by a definite molecular weight or by a molecular weight distribution and also by their shape and size. The most important molecular weight determination method accomplished in the physics of polymers are osmometry or viscosimetry and sedimentation in the ultracentrifuge. The last method is especially widely used for the study of biopolymers. Osmometry is based on the measurement of the osmotic pressure of a polymer solution according to the Van 't Hoff rule. This is the equation where C is equals to solution concentration in grams by centimeter cube, M is equals to molecular weight. It is for equation hold ideal solution. For non-ideal solution, polymer solution are invariable non-ideal. This is the equation for non-ideal solution. A plot of P against the C is linear as and allows us to find M and B. The intrinsic viscosity of polymer solution is defined as this equation where eta is equals to viscosity of solution, eta naught is equals to viscosity of a pure solution. Quantity eta depends on M. Eta is equals to AM. It should be noted that 0.5 lesser or equal to A and lesser or equal to 1.0 depending on the permeability of the coil to the solvent. Fully permeable coil A is equals to 1.0, non-permeable coil A is equals to 0.5, rigid sphere A is equals to 0. Long rigid rods A is equals to 1.7. Sedimentation. Sedimentation method consists of the sedimentation of macromolecule under the action of a centrifugal force in the centrifugal whose rotator revolves at a speed of up to 10 to the power of 4 to 10 to the power of 5 rpm. The centrifugal acceleration is much greater than the force of the gravity g. In modern centrifuges, it reaches 3,50,000 g, 70,000 revolutions per minute. If the rate of sedimentation considerably exceeds the rate of diffusion of macromolecule sedimentation occurs. The macromolecule is acted on the centrifugal force Vm rho m omega square x, where Vm is equals to volume of macromolecule, rho m is equals to density, omega is equals to angular velocity of rotator, x is equals to distance from the axis of rotation. This force is balanced against the frictional force during translational motion. Where calculated per 1 mole, we obtain this equation where Na is equals to Avogadro's number, Vm is equals to rho minus 1, m is the specific particle volume of the macromolecule. For dilute solution, x is expressed in terms of the diffusion coefficient according to the Einstein's formula. X is equals to RT by D. Equation M is equals to RTS by 1 minus Vm rho naught D, where S is the sedimentation coefficient defined by this equation. A sedimentation coefficient of the value of 1 into 10 to the power of minus 13 is called as Swedberg unit. Fixed equation. The diffusion is described by Fick's equation. The concentration gradient and the rate of its change are determined by optical methods. In a special cell, the pure solvent is placed over the solution and the light refraction or interference is studied. The frictional coefficient X depends on the shape of the macromolecule and its permeability to the solvent. For rigid spheres of a radius r, Stokes' law holds. For non-spherical particles, the frictional coefficient are different for the directions of motion that coincide with the longitudinal and lateral axis of the particle. The mean fractional coefficient for a ellipsoid particle is higher than for a spherical particle of the same volume. For long rod-like molecule, the frictional coefficient and viscosity are especially high. Information on the molecular weight and shape of the macromolecule is provided by a optical method of investigation. The intensity of the light scattered by a polymer solution depends on M. Scattering and diffraction. First, small angle X-ray scattering, wide angle X-ray scattering, neutron scattering, dynamic light scattering, static light scattering, and macroscopic techniques. Atomic force microscopy, scanning electron microscopy, transmission electron microscopy, and confocal microscopy. Thermodynamic methods. First, differential scanning calorimeter. Second, isothermal titration calorimeter. Third, vapor pressure oximetry. Other techniques. First, fluorescence resonance energy transfer. Second, circular dichroism spectroscopy. Third, dielectric spectroscopy. Thank you.